All right, so question 23. Twin astronauts conduct an experiment where one travels with a velocity close to the speed of light to a distant planet while the other stays on Earth. Each twin expects the other to be a different age by the time the first twin reaches and remains on the distant planet. Use the theory of special relativity to explain why the twins will no longer be the same age and draw a conclusion about which twin will be younger. So there are 2 marks allocated to this question, and I guess special relativity can be quite a complex topic and difficult to understand. But I guess one of the main and important things to keep in mind when you think about special relativity is that it states that there's no absolute time. And when we think of absolute time, or no absolute time, we think that each frame of reference has their own time due to the one absolute measure being the speed of light. So in a frame that may be moving close to the speed of light, within that frame, light inside it still moves at, let's say, c. Whereas compared to an inertial frame of reference, light is still the same. And when you start thinking about it a little bit more, if you're in that traveling frame and you're traveling near the speed of light, time appears to be slower in your frame of reference compared to, or from the point of view or the perspective of an observer. So I guess there's 2 things. I'm not going to write a paragraph for this solution. I'm just going to put down some dot points for you to keep in mind. Now, you can definitely use formulas to help state your case. So thinking about Lorentz factors formula, thinking about time dilation. We're not going to use length contraction here, but state your case. So this is evidently the twin paradox, but we only have one half of the twin paradox. The full twin paradox is a twin traveling from Earth or from a stationary place. Earth in a lot of these problems isn't assumed to be an inertial frame of reference due to gravity fields and Earth also being an object moving in space. So sometimes they use relativistic measures, saying that the person in the spaceship leaving Earth could be assumed to be stationary and the whole entire universe around them is moving. And that's how you start getting into your ladder paradox as well. But we have, for the twin paradox, one twin is leaving Earth to a distant star or a distant planet and then returns. And the argument is thinking about which twin will be older, the one that stayed or the one that went. In our case, we only have the twin is going to a distant planet and is staying at that planet. With the complete problem, it gets a little bit more difficult to understand and think about because there are portions of deceleration and acceleration as due to the change in direction or movement. So in this case, I would think about, first of all, there is no absolute time. So no absolute time, which is one of our postulates for special relativity. And so I would also state the other postulate, So constant speed of light in each frame. Here I would use my Lorentz factor and say you could assume the velocity for the twin that's moving as it's close to the speed of light. You could say it's 0.0 9c, or 90% of the speed of light, and you could calculate a Lorentz factor out of that. I think from memory, a Lorentz factor of like 0.85, so 85%, will get you a Lorentz factor of 2. And with that, we know our Lorentz factor is our time dilation factor, is another way to think about it. So if 1 year goes by for our person who is moving at the or near the speed of light, 2 years will go by for the observer, or the person in the inertial frame of reference. So then we could make a comment using our Lorentz factor that the twin that is stationary will be older than the twin that traveled. Now, you could also make the other argument that we were talking about beforehand, with the twin that's moving could be assumed to be stationary. And what would be relativistic about that is the twin that was actually initially stationary or stayed on Earth. They were the ones that moved, or the universe around the moving twin, and the rocket ship moved. What I recommend to really kind of wrap your mind around this twin paradox question is there are some good TED Talks or educational TED videos on YouTube about it, as well as having a look at the complete twin paradox, because it does give a probably better breakdown and more time, I guess, to answering that solution. So to finish off, my point would be twin 2. I'd probably denote earlier that twin 2 is the moving twin. Will be older, and I would use my Lorentz factor, or you could just use your time dilation formula, and that will give you your answer.